Hi, this is Sam Jabley, and you're watching Lab 3 Circuits for Physics 2212. So, a quick introduction. In this lab, real circuits will be created using equipment provided so that measurements can be made and compared. The purpose of this lab is to measure values of current, voltage, and resistance via the effects that resistors and capacitors have in circuits. And this lab will showcase the principles of the loop rule, node rule, and Ohm's law. So, some details and results preview before we get started. The system is the circuit, the surroundings is everything else, and the experimental model is the created circuits in the experiment. There is no computational model in this lab, and the node and loop rule were proven true, as well as the usage of Ohm's law as a quick preview of the results. So the fundamental physics principles: Ohm's law, the voltage across a conductor is proportional to the current between 2 points, V equals IR. The loop rule, energy cannot enter or leave a closed circuit, so the sum of differences in voltage around a circuit is 0, and you can see that in this diagram here. And the sum of currents entering a node equals the sum of currents exiting the node, and this is the node rule, and you can see this diagram here. So for the experiment, a real circuit was created for each part of the experiment following the models shown to the right. The first circuit created has 2 resistors and 2 ammeters, and you can see that model here, and it's a 47 ohm and 100 ohm resistor, and then 2 ammeters. And the second model is an RC circuit, and it has a capacitor and a resistor, and you can see this one here, and the resistor is a 47 ohm resistor. And here you can see a picture of the circuit we created. So the batteries were put in series, causing the total voltage to add together. The resistors were put in series as well so that their interaction with the total voltage could be analyzed. And the charging and discharging of a capacitor with time were analyzed with the normal circuit and the RC circuit. The total resistance and voltage in the circuit were calculated by summing the respective quantities together within the circuit. Using Ohm's law, the theoretical current was calculated, and then the actual measured current was calculated using measured amounts of resistance. And you can see the calculations for that over here. The total voltage drops by 2.9 volts from point C to the end of the loop, so the total delta V across the loop is 0.1 volts, and you can see that here. And here you can see a little diagram of the measured voltages across all the points that we took. So for part 2 of the experiment, the RC circuit, the RC circuit was created using a 1F capacitor and a 47 ohm resistor. The charging and discharging times were measured with a stopwatch, and the linearization equation to the right was utilized in creating a plot with a slope of -1 over RC, over the RC constant. And here's the linearization equation, and here's the slope. The time to charge the capacitor took 1 minute and 10 seconds, and the time to discharge the capacitor took 52.79 seconds. And both were measured using a stopwatch. Attaching the voltmeter alters the circuit, but does not change the ammeter reading since the voltmeter has high resistance with little current flowing through it. So the assumptions and errors. The assumptions are that resistance within the wires is negligible since it is not a significant number, and that the resistance in the ammeter is also negligible. And the errors in measurement and timing in the experiment, so human error basically. And there likely is deviation in the resistance in the ammeter and wires from the theoretical values, as there likely is more in real life than theoretically. So some similarities between the observed versus predicted. The current was the same throughout the circuits in both models, as well as the voltage prediction and calculation. The loop rule was satisfied in both the observation and prediction models. And the differences were that there was some deviation between the beforehand calculations using background formulas compared to the actual experimental model as a result of human error and internal resistance in the battery and wires. So, what if you charged a capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge, and would this prediction happen in real life? The model would predict that the capacitor charging to full charge would be very rapid. This prediction is not necessarily realistic, however, as resistance within the wire and other internal resistance would likely cause deviation from the prediction in the model. And that concludes this lab. Thank you for watching, and I hope you learned something. I'll see you in the next one.